All right, let's take a look at our lesson for today. We're going to be looking at two different topics, removing discontinuities and IVT, which is the intermediate value theorem. Okay, so let's talk about removable discontinuities first. This is a fancy word for hole. Okay, these are holes. That's a removable discontinuity. So why would they call it removable? What does that even mean? So we want to know why. Why is it removable? Well, it's removable because, and I'll just write this out, because you can rewrite as a piecewise function and remove or plug the hole. So that is certainly possible. So let's talk about an example. Okay? So, because I don't think I have an example where we remove the hole. So let's do an example where we remove the hole. What in the world am I talking about? Yes. Just put your cursor right there. Your what's it called? There you go. Okay. So let's talk about what does it mean to remove the hole? What does that mean? Okay, so let's look at an example. Let's say our equation, our f of x would be, I'm going to factor it. So I'm going to use this picture, but I'm going to make let's make it like 3. Okay, for this circumstance that I'm making up a problem where a is 3. All right, so we've got this going on, okay? Let's say it looks like this. All right, so we can see that when we cross this out, right, if you remember from your pre-cal days, when you eliminate a factor, that creates the hole, right? That's what happens. We have a hole at 3. So how would we plug the hole? It's basically the same thing as finding out what the y value of the hole is. So how do we do that? We plug in. So we've got that simplified. Now our f of x is simply, x minus 2. We want to find out what f of 3 is because that's where the hole is. So we have 3 minus 2 or 1. All right, so the y value of this hole is 1. Okay, so how would we plug it up? How would we rewrite it? So what we would do is we would say, write as a piecewise, so f of x equals, we would say it's this original function, the x minus 3, x minus 2 over x minus 3. It's that every time except for when x is not 3. It's that every other time except when x is 3. Then we're going to choose a y value of 1. And why did I pick the y value of 1? Because that's the y value of the hole, right? So I'm basically removing it by saying it's 1 when x is 3. So when we graphed it, it would look like this, and then we would simply fill in the hole, right? And it would be continuous. That's why it's called a removable discontinuity. It's a hole that we can rewrite. So here's this is what we would do. We would rewrite it and plug in the hole. Okay, questions on a removable discontinuity? Any question? Okay, so that's one topic for today, is removable discontinuities. The second one, which is really going to take up most of our time, is a new theorem, intermediate value theorem. All right, intermediate value theorem. So this is a big deal, the intermediate value theorem. We have three. So if you recall from geometry and theorems, we have our hypothesis. So that our if is the hypothesis. If these things are true, then this part is our conclusion. And that's how we worked theorems in geometry. We had a hypothesis and a conclusion. So let's look at this theorem and the hypothesis and conclusion, and let's figure out how it works. All right. So first up, it says f has to be, so we need a closed interval. This is a closed interval, from whatever number. So here's our closed interval. So the first part of the hypothesis says that the function has to be continuous on the closed interval. And we can do this by inspection. We can do this by inspection. Let me talk about what that means. What does by inspection mean? It means I can look at the equation, and because of my mathematical knowledge, I can determine whether it's continuous or not. There's no work that I have to show. I just have to state that it's continuous on the closed interval. Okay, so we just use our mathematical knowledge. That's called, we do it by inspection. We look at it and we say, okay, f is continuous on the closed interval. So that has to be true, or the theorem does not work. The second thing that has to be true is that the y values of the endpoints have to be different. They have to be different. The y values of the endpoints have to be different. And if they're not, we can't use the theorem. The last thing that has to be true is that k, and let's talk about k. K is a y value. And a lot of times they tell us what k is, and sometimes they don't. We're going to do several examples so you can have figure out when we know what k is, when we don't. So k is a y value. And that y value has to be between the beginning y value and the ending y value. It has to be. Okay, that y value, whatever k is, has to be between the beginning y value and ending y value. And if that's true, then our conclusion is there exists a number c, and c is an x value. There exists a number c between a and b. This was our interval from the beginning, for which f of c equals k. And c, that's our x value, and that is the y value. All right, so that's the theorem. Okay, so I'm going to make a note. First of all, I want to pause here for a second. Are there any questions about the theorem itself? So we understand the three parts and the conclusion. And I'll show you how it works. We have several examples. But I'd like to make a note. This is a note. And this is going to help you on assessments and on the AP test. When using this theorem, in your work, you must use the numbers from the problem. Okay, you have to. Okay? So if you don't, use the numbers, I'm making a big deal of this because I see this over and over again. If you don't use the numbers from the problem, you will not get credit for knowing it. You will not get credit for knowing IVT. Knowing/using IVT. That's how important this is. Okay? So what I'm saying is you can't just say f is continuous on the interval a to b, f of a. In the work you have to write f is continuous on the closed interval -1 to 5 or whatever the actual interval is, and f of -1 doesn't equal f of 5. I mean, you have to actually use the numbers. You can't use the a's and the b's and the c and the k. You can't use those numbers. Does that make sense? Mm-hmm. Yeah, you have to actually use the numbers, because what I find is that students just like to repeat the theorem because you've memorized it, right? And if it doesn't have the numbers in it, it won't make any difference. You won't get credit for it. Okay? All right. So are we okay so far with the theorem? All right, so let's work some problems. Okay, so this one is working on, so we're saying G is that piecewise function, A is a constant, some number, we don't really know what it is, but it's a number. For what values of A, if any, is G continuous at x equals 1? All right, so let's talk about this piecewise function. So this is a parabola. Are parabolas always continuous? Yeah, isn't it? Isn't it just like a U looking thing? Either the face is up or down. It just always goes, right? Yeah, all x's work. So this is okay. This is just a number, right? And this is a line. Are lines continuous? Yeah, there's no holes in lines, right? It's fine. So where is our danger? Our danger is when they connect. So this part right here is where the danger lies. This is where the function may not be continuous. Okay, that's where they connect together. So by themselves, they're okay. It's just where they connect together, we have to be careful. So what do we have to do? Well, what we have to do is we have to take the different pieces. So for example, I'm going to, let's erase this for right now because we're talking about that. So I'm going to connect these two things together. And after I'm done with that, I'm going to connect these two things together. I have to do both sides. So what does that mean? Okay, I'm going to have to say x squared plus x equals a when x is 1. I don't really care if they're equal any other time. I don't care. I only want them to be the same when x is 1. Why did I pick 1? Because that's where they join together, right? That's where the two functions become 1. So I'm going to plug a 1 in for x. So I've got 1 squared plus 1 equals a. So for the top two functions, if a is 2, we're in great shape and we're continuous. Okay, so when a is 2, so I'll write this down. If a is 2, then the top two pieces of the piecewise are continuous. They hook together. Okay, that's what that means. Okay, is everybody okay with that? So if I made a 2, then x squared plus x, the parabola and the point would join together. We'd be happy. All right, so that's for the top, but that's not enough. I also need to know if that a connects with the bottom piece. I need to know that too. So I've got to say 3x plus 5 equals a when x is 1. And again, I'm specifying when x is 1 because that's when those connect together. All right, so let's do that. So we're going to make x 1, so 3 times 1 plus 5 equals a. So 8 equals a. So let's write ourselves a note. If a is 8, then the bottom two pieces of the piecewise are continuous. Okay, well, that's nice, but what about the whole function? Is there one value of a that would make all of g continuous? No, because those numbers are different. So we'll write our conclusion. So since the a values are not the same, there is no value of a that will make g continuous at x equals 1. Okay, since the a values are not the same, there's no value of a that will make g continuous at x equals 1. All right, how are we doing with that? Everybody okay? All right, great. Any questions? Okay, let's look at the next example. This example has to do with continuity also. And this is similar to the problems in AP Classroom. I actually took this from AP Classroom. It's not one of the ones I assigned you, but this is similar. So let f be the function defined above, where a is a constant. For what values of a, if any, is f continuous at 3? Okay, so let's just make ourselves some notes. This is a parabola. Our parabola is continuous? Yep, so I don't have to worry about that. This is a line. Are lines continuous? Yep, don't have to worry about that. I only have to worry about where they connect. That's all I care about. Where they connect, okay? So we're going to take each piece, a squared plus x squared equals a times x plus 3 when x is 3. Again, why do I care? Why am I making them equal to each other when x is 3? Because that's the dangerous part. That's when it might not match. They may not be continuous. So we have to force it. Okay, that's what we're doing. So now we're going to plug in a 3 for the x. So I have a squared plus 3 squared equals a times 3 plus 3. All right, so let's keep working it. So I've got a squared plus 9 equals, let's see, 3 plus 3 is 6, 6a. Here's where our pre-cal / algebra skills come in handy. To solve that, I'm going to have to move everything to one side, set it equal to 0. That's what we do when we solve. We move everything to one side, set it equal to 0. So I've got a squared minus 6a plus 9 is 0. And then that's a quadratic. We've got lots of different ways to solve quadratics. What's one way we could use? Factoring. Yep, factoring like FOIL, right? We could factor like FOIL. So that's what we're going to do. Let's hope. Otherwise, we're going to have to do quadratic formula, right? So let's hope for factoring. I think factoring is probably going to be fine. Let's see, the back sign is positive. That means the signs have to be both negative because the middle one is negative. What is that? 3 times 3. Yeah, so A is 3. Okay, so A is 3. So my answer is this one, 3 only. All right, and those are the problems on continuity. We doing okay? Okay. The next two or last two problems are on IVT, intermediate value theorem. Okay. So this problem number 3 does require a calculator. I used a calculator. You don't have to get your calculator. I'm just telling you, to do this problem, you would need a calculator. And there's a little bit of a typo here. See that should be a point, not a comma. That's a point, not a comma. I went a little crazy when I was typing. Okay, so here we go. Suppose that you invest $1,000 in a special 5-year savings account with a fixed annual interest rate R. Okay, let's just make ourselves some notes. This is interest rate R with monthly compounding. The amount of money A in the bank after 5 years, and they're equating this for us, 5 years is 60 months, is, so this is the equation that we're going to be working with. Okay, that's fine. We would have a calculator, so we don't have to do that in our head. Your goal is to have $1,400 in the account after 5 years. Use the intermediate value theorem to show there is a value of R between 0 and 0.08, that is an interest rate between 0% and 8% for which A of R is 1,400. Okay, so we're using the intermediate value theorem and we're going to walk through the steps. Step number 1, and yes, this is something you would have to memorize. It's on a formula quiz. Okay, so here we go. Step number 1, our function is A. So I'm looking for continuity. I'm looking for continuity from 0 to 0.8. So by inspection, I'm looking at this. If I put any number between a 0 and 0.8 here, would I be okay? Am I going to get a number? Yeah, I'm okay. I'm okay. So A is continuous. From 0 to 0.8. Step 1, continuity. Step 2, I need to find A of 0, and I need to find A of 0.08, and I would use my calculator for that. Okay, I need to find them. I need to see if they're the same number or not. That's what I need to see. So A of 0, I use my calculator, I plug a 0 in for R, and I get 1,000. A of 0.08, I plug 0.08 in for R, I use my calculator, and I get $1,489.85. So in step 2, I say 1,000 does not equal 1,489.85. Step 2, the y values of the endpoints are not the same number. Okay, step 2. Step 3 is K is between f of A and f of B. Well, K is, let's just make ourselves a note right here. This little thing right here is K. 1,400 is K. Why? Because our goal is, in this context, our goal is to have 1,400. That's what we want. Okay, so we will say 1,400 is between 1,000 and 1489.85. Notice how I'm putting numbers into the IVT. That's what I meant by you have to use the numbers from the problem, or knowing it is not enough. It's not enough, okay? So now some students are like, well, could I write it like this, like 1,000 less than 1,400 less than 1489.85? Yes, you could write it like that too. Either one of these statements is sufficient for step 3. Okay, either one, whatever you like. So since the hypothesis of the intermediate value theorem is true, that means the conclusion is also true. So we would say, therefore, there exists a number C between 0 and 0.08 for which f of C equals 1,400, because that's my K. And that's intermediate value theorem. What do we use it for? We use it to prove things. This is an example of proving something. All right, questions on that use of IVT? And please notice that everywhere there was an A and a B, I'm putting actual numbers, right? I'm putting actual numbers in here. I am not using the A and the B and the C and all that. I'm putting numbers in there from the problem. Okay? All right, we have one more intermediate value theorem. We good? Okay, let's do our last intermediate value theorem. Use intermediate value theorem to show that the following equation is a solution on the given interval. Okay, so first of all, we're going to do math talking. Okay, this word solution. This can also, other words. We need to look at other words for solution, because this kind of problem is very common and they don't always use the word solution. Sometimes they use the word root. Other words that they would use here is a root or a zero. They all mean the same thing. What does it mean? It means where the function crosses the x-axis, right? These are roots or zeros. That's what it's talking about, or solutions. That's the same thing. So that's what they want us to know. Look at all those roots and solutions. What value do they have in common? The things that I've circled on the graph, what value do they have in common? 0, right? The y value is 0. All of these have a y equals 0 value. So that's a sneaky way of telling us what K is. That is a sneaky way of telling us what K is. So with that information, we know that K is 0 in this problem. That's what we want. We're trying to prove that that exists. All right, so now let's go through all the steps of IVT. Step 1 is the continuity step, right? And actually, I think to make our lives easier, and this is also perfectly fine on the AP test, you can, if it's not named already, you can name it. Let's just name it so our work is a little bit easier. Okay, f of x is going to be 2x cubed plus x minus 2. You can call it something else, g of x or h of x, or I don't know, the first letter of your name of x, whatever you want to call it. All right, so step 1. F of x is continuous, because it's a cubic, right? They're always continuous, from -1 to 1. And I can abbreviate continuous. That's an okay abbreviation. Or you can write the word out. It's fine. Number 2, I need to find f of -1, and I need to find f of 1. I need to find them and show that they're different. You have to write the values there. You can't just say f of negative 1 doesn't equal f of 1. That's not enough. You have to show the values. All right, so f of negative 1, I actually did arithmetic. I know, crazy, right? F of negative 1 turned out to be negative 5. So what did I do? I went in there and I plugged in a negative 1. F of negative 1 is 2 times negative 1 cubed minus 1 minus 2. That's what I did, and I got a negative 5. I just did this work over to the side. You know, f of 1, I plugged a 1 in, cubed plus 1 minus 2, and I got a 1. So I have to say negative 5 does not equal 1. You have to put that part. You can't leave it out. All three of those things are necessary for step 2. The number values and saying they're not the same. Is that okay? All right, step 3. K has to be between negative 5 and 1. Is 0 between negative 5 and 1? Yes. So 0 is between, and you can abbreviate between, negative 5 and 1. Or again, you can write it as an inequality if you would like. So since those three things are true, therefore, we're going to use the word they did. They used the word solution, so we will. Therefore, there exists a number C between negative 1 and 1 for which f of C equals 0.